14th lecture. We are studying Markov process for the last couple of lectures, and we'll continue studying the same even in this lecture. In this video, we will solve an example where we are given a chain, a Markov chain or transition probability chain. This chain contains 4 states, and we see that probabilities of transfer between states is given. And we also know that we studied in last lecture that the sum of probabilities of ij or j in the set S is the state space of all the chains is 1. This means the sum of all the arrows, and this is for all I. This means that all arrows that move out of a state, they sum to 1. For example, for this 2, this is 0.4 plus 0.3, 0.7 plus 0.31. So for every state it can be verified. Right, a process is a discrete process where at each time, suppose Tn, if the state of the process, for example, for this time Tn, if the state is 1, it can be a state T at n plus 1. It can be the same or different state, but in this chain, if the state at time Tn is 1, so it remains 1 only in this case. But if it is 2, it can remain 2 at n plus 1, or it can be 0.3 with 3.3 probability. It can be 3, and with 0.3 probability it can be 1. So, but the state cannot be 5 because 5 is out of the state space. So the state can be one of these 4 numbers at any given time in the process. In the process, we have assumed it goes on and on. It goes on and on. Right. What is TPM? TPM is transition probability matrix, or it can also be written as state transition matrix. This involves probabilities. This P11 is the probability that we started from 1 at Tn plus at Tn, the state was 1, and what is the probability that it will be 1 at time n plus 1. P12 means that it was 2 at n. What is the probability that it will be 1 at n plus 1? So we have studied Pij in general. Pij in general in last lecture. Pij. Right. So, and we also studied that this state transition matrix or transition probability matrix is always a square matrix with size m cross m, where m is the number of states in the state space. Here, 4 states, therefore the size is 4 by 4. The size of the matrix is 4. Right. So now we are going to fill some missing probabilities by looking at this chain or diagram. Right. Starting at 1, and we also studied that we're writing it in such a way that the sum of all the probabilities that we write in a row, they should sum to 1. So the output, the sum of each row sums to 1. Right. For the first row of the TPM matrix is that if we start from 1, what is the probability that we'll end up at 1 at n plus 1 at time n plus 1? If we start at time n, we are at state 1. What is the probability that we will be at the same state 1 at time n plus 1? It shows it is of 1. And if we start at 1, what is the probability that will be at n plus 1? It will be at state number 2 at time n plus 1. It is 0, because there is no outgoing arrow, and it cannot be, because this 1, this means we cannot have any other arrow merging out of 1, because sum of all outgoing arrows is of 1. Right. For state state 2, if we are at state 2 at time tn, what is the probability that will be at n plus 1 will be at 1? That is 3. Add 2 is 0.4, will be at 3.3. But if we are at state number 2, we cannot be at state number 4 at time n plus 1, because there is no from 2 to 4. If we are at state number 3 at time tn, that we are at state number 1 at time tn plus 1. There is no outgoing arrow from 3 to 1, therefore it's 0. From 3, starting from 3 at time n, we'll be at n plus 1. We will be at state number 2 at time n plus 1 with probability 0.3. And starting from 3, we will be at 3 at time n plus 1 with probability 0.3. And it's not 0.3, sorry, it's 0.4. We'll be at 3. Starting from 3, we will be at 3 with probability 0.4. And starting from 3, we'll be at 4 with probability 0.3, right? And for state 4, go anywhere, because we are trapped in 4. So there are two trapping states here, state number 1 and 4. Once they are there, we cannot go out of them. So this is 1, all others are 0. Right. The process visualization is that it's a process going on, and if I am at state number 1 here, if I am at state number 1 here, at state number 1 here, I will be at state number 1. Right, I will be at state number 1 at n plus 1, and I will be at state number 1 for all states to come. I cannot be otherwise, because once I'm at state number 1, I cannot go out of it. State number 1, I'll remain in state number 1 forever. But if I start from state number 2, I can be at state number 3 with some probability at time tn plus 1. I can be state number 3. I can be at state number 1, and I can finish up at it at the same state with different probabilities. So start, can be at 3, 1, and 2. Right. This is an example. And then you can, if I'm at 3 at time n plus 1, at time n plus 2, I can be at state number 2, I can be at state number 3, or can 4. But if I am at 4, I'm trapped there. I cannot go out of it. And then for all times to come, I'll remain at state number 4. Right. One last item for today is that all probability values that we write in this TPM. In TPM, TPM. TPM is transition probability matrix. In this TPM, all these values that we write here are conditional probabilities. Pij is probability of xn plus 1 equals j given x is equal to I. So in our next lectures, we'll see how we can use these to figure out joint figure out joint probabilities and marginal probabilities using the conditional probability terms that we find in TPM matrix. And in the upcoming lectures, we will also study steady state probabilities of Markov chains. Steady state probabilities. So that's all for today's lecture. Thank you for watching this video. Thank you.